Okay, well, I'm going to try a different quality video capture because the first one was low quality, and I apologize for that. I will see if this one does any better. It's going to take up more gigabyte, more RAM, but that's okay. I'm putting it on YouTube, and hopefully it will work out for them. Take me a little longer to upload. Okay, so we're on slide 21, halfway there on chapter 4. We're talking about winds in the upper atmosphere, gradient flow. We're in the upper air, moving from areas of high pressure to areas of low pressure. They undergo that Coriolis deflection that we mentioned already. Coriolis force in the upper planetary boundary below the free atmosphere. Okay, just to refresh your memory. The air will eventually flow parallel to the height contours as the pressure gradient force balances with the Coriolis force. So Coriolis force greatly affects the winds. It causes a rotation. Next slide regards, there are some supergeostrophic and supergeostrophic flow. So what's supergeostrophic versus supergeostrophic flow? We're talking about, in those terms, high pressure areas. High pressure, what do I mean? Well, it's above sea level pressure. It's above 1,000 millibars for sure, and it's the highest pressure in the planetary boundary layer. Okay, so the air undergoes rapid acceleration, and the Coriolis force dominates the pressure gradient force. In other words, it's in the planetary boundary layer, and it produces a supergeostrophic condition. Alright? In other words, rapid acceleration, Coriolis force is dominating the pressure gradient force. Alright? Around low pressure areas, supergeostrophic conditions occur as the pressure gradient force dominates the weaker Coriolis force. So you can imagine that at higher altitudes, supergeostrophic conditions can exist, as well as at lower altitudes, depending on the pressure gradient force with respect to the Coriolis force. So both supergeostrophic and subgeostrophic conditions result in airflow parallel to curved height contours. Okay, so subgeostrophic and supergeostrophic, to me, I identify them as supergeostrophic. But let me recap with you. Supergeostrophic is when the Coriolis force dominates the pressure gradient force. Subgeostrophic is when the pressure gradient force dominates the Coriolis force. Simply put. Okay, so with super and subgeostrophic flow, we show you in super geostrophic we're mainly looking at the surrounding areas with high pressure causing it. Subgeostrophic, the surrounding areas caused by a strong low pressure area. Slide 24, near surface winds, they're slow due to friction, and so they're not parallel to any isobars. Okay, they actually cross isobars because of friction. Friction is stronger. Coriolis deflection still occurs, but it is reduced. Alright, those are vectors in the slide. If you have any questions about those vectors, it might seem relatively clear, but PGF stands for pressure gradient force. And notice that the force is moving from high to low. That's going to be the case. And notice that the wind might take a different direction because it's close to the surface of the earth. Friction is causing the wind to take a different direction. That's all we're talking about there. So next slide regards the time when the isobars are very close together in anticyclones, cyclones, troughs, and ridges. So let's take anticyclones for example, something that you may not be aware of. High pressure areas are called anticyclones. They have a clockwise airflow in the northern and a counterclockwise airflow in the southern hemisphere. It occurs as air diverges from the high pressure at the surface and is deflected by the Coriolis force. So it starts at the surface, starts rising, and the Coriolis force gets stronger as the air rises, causes a counterclockwise in the southern and a clockwise in the northern. Okay, rotation. So it's also always characterized by descending air that warms and creates clear skies. So let me just use my hands. The air is moving down like that. Okay. And in the northern hemisphere, it's not only moving down, but it's moving in a clockwise fashion. Alright, moving on. Anticyclones, cyclones, troughs. So what is a cyclone? It's the opposite of an anticyclone. Alright? So notice anticyclones have a clockwise rotation. Notice where we switch in those pictures. Slide 27. Cyclones. Air converges toward low pressure centers. Okay, those are called cyclones, and they have ascending air, which cools, and they form clouds. This is the cyclones. The low pressure centers are where we get our storms, precipitation. The upper atmosphere corresponds to the ridges of the cyclones. They correspond to the surface anticyclones, while troughs correspond to the surface cyclones. Alright, ridges, high pressure, troughs, low pressure. Alright, when you're looking at a large area, which is the way you need to look at a weather map, you see ridges and troughs. Ridges are high pressure, troughs are low pressure. Where the ridges are, you can get the anticyclones. Where the troughs are, you can get the cyclones. Okay? And so, slide 28 shows you the cyclones. Notice they're moving counterclockwise in the northern, clockwise in the southern. Back up to slide 26. Anticyclones clockwise in the northern, counterclockwise in the southern, and then to slide 28, cyclones counterclockwise in the northern, clockwise in the southern. Just got to remember that. Just remember one hemisphere. Oh, how about the one you're in? Northern hemisphere. Troughs and ridges, again, slide 29. Again, I'm just reiterating the fact that we're talking about low and high pressure systems. Low for trough, ridges high. Alright, and they're elongated. They're distributed as cyclones and anticyclones. They give way to the ridges. The ridges and the troughs are in the upper atmosphere. In the surface, the surface bows to these strong systems. Notice how the contour lines, the isobars are close together in these areas. Alright, slide 31. More weather maps. Like I promised you, I'm going to give you weather map after weather map after weather map. And I want you to get familiar with these weather maps. You see how sometimes the isobars are close together. Remember what that means. And if you determine which way the pressure is decreasing or increasing, will tell you which way the wind flows. Okay? And we might have a little fun with that next class. So get familiar with these. Might have a pop quiz, so get ready for it. I might throw some of these up at you, and you're going to have to tell me which way the wind blows. Alright? So, slide 32, measuring the wind and the wind direction. It indicates the direction from which wind blows. So, from which wind blows. That's the important part there. Alright, so azimuth. What is an azimuth? Well, that's the direction in degrees, okay? Angles. So we measure north is 90 degrees. Alright? Or, I'm sorry, north is the beginning of a circle on the earth. We measure that as 0 degrees for our azimuth. And anything to the right of north is positive degrees. Anything to the left is negative degrees. Or we could say north to east. East is 90 degrees of north. Alright, anything in between 90 and 0 is something like northeast or east-northeast. You understand? Then if I move to the left of north, my left, your left, left of north, then we were looking at anything from west, which is at 270 degrees, to north, which is again 0 degrees, or 360. Alright? And if you have any questions about that, if you're not familiar with it, come and talk to me. It's not that hard. Just what I recommend is you start off at north at 0 degrees and work your way to east, which is 90 degrees, and then to south, which is, what do you think, 180 degrees maybe? And then west, again, is 270 degrees, and back to north, which is a full 360. That's how you can remember it. So if you go clockwise, north, east, south, west, back to north, you can remember 0, 90, 180, 270, 360, or 0. If you use that direction, you're good. Okay, for your azimuth. Now, wind vanes, they're devices that we measure the wind speed and direction with anemometers. Alright, we have what's called stations, station models with wind vanes and anemometers, also giving us azimuth, density, pressure, and temperature. So you see how it's all working together? And so it goes even farther. Water content in the air, moisture content, relative humidity. It goes on. Alright. Elevation. So aerovanes, they measure both wind and direction, wind speed and direction. So there's a typical one on slide 33. And the azimuth is also provided to you there to kind of refresh your memory what I just went through with you. Okay. That's chapter 4. So that ends part 2 of 2 parts to chapter 4. We'll pick up on chapter 5, take a break, and we'll pick up on chapter 5.